summer 1940. Royal Air Force Hornchurch Airfield, Essex. Two identical Supermarine Spitfires stood glistening in the morning haze on the concrete apron. Same Merlin engine, same 8-gun armament, same pilot strapped into the cockpit. Squadron leader Desmond Cook throttled up the first aircraft. Takeoff run 320 yards, climb to 20,000 feet, 11 minutes and 8 seconds. Service ceiling, 32,000 feet, where air grew thin and engines gasped for oxygen. 20 minutes later, Cook climbed into the second Spitfire. Identical airframe, identical engine, but a different propeller. Takeoff run, 225 yards. Climb to 20,000 feet, 7 minutes and 42 seconds. Service ceiling, 39,000 feet. The same plane, the same engine, the same war hanging in the balance. Yet the outcome of the Battle of Britain, the survival of a nation, would hinge on 3 spinning aluminum blades that aviation experts across America had dismissed as impossibly complex. Frank Caldwell's impossible propeller had just revealed itself in the English sky. But the story of how one quiet engineer's numbers defeated an entire industry's assumptions began 8 years earlier, in a factory where everyone told him it would never work. Frank Walker Caldwell stood inside the oil-stained test facility of the Hamilton Standard Propeller Corporation in East Hartford, Connecticut, on a grey February morning in 1932. At 43, the MPH-trained engineer carried the methodical air of a man who trusted numbers more than opinions. His wire-rimmed glasses sat low on his nose, clipboard tucked under a calloused hand. Behind him, a new kind of machine screamed to life. A gleaming metal propeller spinning at 400 revolutions per minute, mounted on a vibrating test stand that rattled the floor. 3 aluminum blades that could change their angle while rotating. Something that had been called impossible. 3 days earlier, a phone call from Boeing Field in Seattle had changed everything. The Boeing Model 247, America's revolutionary new twin-engine airliner, sat stranded at Denver Municipal Airport like a champion horse with a broken leg. At 280 feet altitude, the aircraft could barely climb over the Rockies. 2 fixed, pitch wooden propellers, each locked at one optimized angle, rendered the aircraft nearly useless outside of ideal conditions. That morning, Pan American Airways President Juan Trippe delivered an ultimatum: fix it, or we're buying Douglas. The stakes couldn't be higher. United Airlines had 25 Model 247s on order, and Transcontinental and Western Air wanted 30 more. But none of that mattered if the plane couldn't cross the Rockies. Across America's aviation community, the consensus was as firm as doctrine variable: pitch propellers were unnecessary. Too heavy, too complex. Too many moving parts in environments where vibration, freezing oil, and altitude would destroy delicate mechanisms. The U.S. Army Air Corps Engineering Division had even classified Caldwell's design as mechanically unsound. Even Charles Lindbergh, aviation's most celebrated voice, had questioned it during a meeting at Wright Field the previous fall. But Caldwell had been proven right before. As the government's chief propeller engineer from 1917 to 1928, he had fought similar battles, first for metal blades when the world swore by wood, then for adjustable pitch props when simplicity was gospel. Each time data had demolished assumption. Now, with Hamilton Standard's survival tied to his untested design, the stakes were existential. 800 jobs, dozens of suppliers, and his own career rested on those 3 blades and a hydraulic governor system that used engine oil pressure to automatically adjust blade pitch in flight. The theory was beautiful. During takeoff and climb, the blades turned to a fine pitch, like a car in low gear, allowing the engine to spin fast and generate more thrust. At cruising altitude, they automatically shifted to a coarse pitch, optimizing for speed and fuel efficiency. If an engine failed, the blades could feather, rotating edge, onto the airflow, eliminating drag that would otherwise spin the aircraft into a deadly spiral. Caldwell's wind tunnel tests at MIT showed results that should have silenced every critic: climb rate up 40%, service ceiling higher by 7,000 feet, fuel efficiency better by 15%. But numbers meant nothing if the world refused to believe them. February 15, 1933, United Airlines President Pat Patterson gave Hamilton Standard one last chance: a single test flight on a Boeing 247. Test pilot Eddie Allen, a calm, methodical former Navy flyer, took the controls. The aircraft lifted from Denver and began to climb past 6,000 feet, the altitude that had defeated the previous 247, then 8,700 and kept going. The constant speed propeller automatically adjusted to altitude, holding perfect engine RPM and steady thrust. It crossed the continental divide effortlessly. Where the old fixed-pitch 247 had struggled to reach 6,000 feet, the modified aircraft soared to a service ceiling of 2,700 feet. Cruise speed, 15 miles per hour faster, fuel economy 20% better. That evening, a telegram arrived at East Hartford. Constant speed propeller exceeds all performance claims. Recommend immediate adoption for entire United Fleet. But even as orders flooded in, darker clouds gathered abroad. In Germany, the Nazis had seized power. In Japan, military leaders spoke of Pacific domination. What began as a tool for passenger comfort was about to become the weapon that would decide air superiority. May 1933. The phone rang in Caldwell's office. Commander John Towers, U.S. Navy Bureau of Aeronautics. The voice said, "We need faster fighters, and bombers that can fly higher than enemy interceptors." A war was coming, and Caldwell's invention held the key. That November, a telegram brought stunning news. The National Aeronautic Association had awarded the Collier Trophy to Hamilton's Standard for development of the controllable pitch propeller, with particular credit to Frank W. Caldwell. President Roosevelt himself would congratulate him at the White House. But not everyone celebrated. At Wright Field in Dayton, skeptical Army pilots grumbled that complexity kills. Major Benjamin Kelsey of the Air Corps Fighter Projects Office put it plainly. What happens when that hydraulic system fails over Germany? Caldwell's answer was data. He built a new test facility at East Hartford and invented what became known as the Whirl test. A device that spun propellers under extreme loads, measuring thrust, endurance, vibration, and failure points far beyond combat conditions. His hydromatic propeller used engine oil pressure to move a piston that rotated the blades through gears and counterweights. A small centrifugal governor, no larger than a coffee can, automatically maintained constant RPM regardless of airspeed or altitude. If the aircraft climbed and the air thinned, the propeller moved to fine pitch. If it dove, the system shifted courser to prevent overspeed. And if an engine died, the blades feathered instantly. For bomber crews, that could mean survival. The numbers told the story. In tests, a P-51 Mustang with Caldwell's constant speed propeller versus one with fixed pitch showed staggering differences: 30% shorter takeoff distance, 40% faster climb, 7,000-foot higher ceiling, 200-mile longer range, 15% better fuel use. But Caldwell's obsession wasn't speed, it was reliability. He demanded every propeller survive loads 50% beyond combat stress. Governors ran continuously for 500 hours in heat from 160 degrees F to 40 degrees below zero. Oil seals were fouled intentionally with debris to mimic neglect and battle damage. Meanwhile, rivals like Curtiss Wright attacked relentlessly. They claimed his design was too delicate for war, publishing papers warning that hydraulics will freeze at altitude. Caldwell answered with more numbers. At 35,000 feet, cold weather tests proved thicker oil actually improved response precision. Vibration data showed constant speed systems suffered fewer failures because their self-adjusting blades avoided resonant frequencies that shattered fixed hubs. March 21, 1934, Selfridge Field, Michigan. Two identical Boeing P-26 fighters took off side by side. One used a fixed-pitch propeller, the other, Caldwell's constant speed system. At 10,000 feet, the fixed-pitch fighter arrived in 8 minutes 30 seconds. The constant-speed aircraft, 5 minutes 40 seconds. Top speed 107 miles versus 2T3. Ceiling 28,000 feet versus 34,500. Lieutenant Colonel Carl Toohey Spatz, later commander of U.S. Strategic Air Forces in Europe, wrote in his report that the performance difference represents a fundamental shift in combat capability. By the end of 1934, Hamilton Standard's production lines ran 24 hours a day to meet the avalanche of military orders. But while Caldwell refined his miracle propeller, Europe slipped toward war. In Germany, the Luftwaffe's new Messerschmitt Bf 109 fighters still relied on manual pitch control. Pilots had to adjust blade angle themselves during combat. In Britain, Spitfires and Hurricanes used primitive two-position propellers, one for climb, one for speed, nothing in between. The results were deadly. In 1939, RAF combat reports told the grim truth. German fighters outclimbed British aircraft above 15,000 feet. British bombers aborted missions when they couldn't clear mountains. Pilots lost seconds fumbling with manual pitch levers, the seconds that meant life or death. Air Marshal Hugh Dowding, commander of Fighter Command, feared the worst. Britain's fighters were technologically outmatched. At a 1938 conference in Detroit, Caldwell presented comparative data showing climb rate up 35%, fuel economy up 15%, and combat ceiling higher by 6,000 feet with constant speed control. But European engineers dismissed it. Germany's Dr. Ernst Heinkel mocked it as American over-engineering. British manufacturers insisted manual control was simpler and safer. By 1939, as orders poured in, Hamilton's Standard faced impossible demand. Each propeller required 47 precision, machined components, every tolerance measured in thousandths of an inch. Caldwell's factory ran 3 shifts, 7 days a week. Still, demand outpaced supply. Then disaster struck. A batch of defective governors caused 3 propeller failures during tests at Wright Field. Exactly the conditions most feared. Army procurement threatened to cancel 12 million in orders. Caldwell's response: redesign everything. In 6 weeks, his team built redundant hydraulic circuits, backup mechanical locks, and implemented 50% higher stress tests. He personally signed off every propeller that left the factory. By early 1939, his system was bulletproof, and just in time. The Luftwaffe now had 4,000 aircraft. Britain fewer than 700 fighters. As the Battle of France began, RAF squadrons with outdated propellers found themselves helpless. German fighters could climb away at will above 15,000 feet. Flight Lieutenant Douglas Bader wrote bitterly, "Their planes just walk away from us. It's not skill, it's the propellers." Losses mounted. By June 1940, with German forces massed across the Channel, the RAF faced a choice: adapt or perish. June 16, 1940, Rolls-Royce Factory, Derby. The hum of lathes and milling machines filled the air as engineers studied the latest performance charts from RAF squadrons. The numbers were catastrophic. A Spitfire MKI with its old 2-pitch propeller could climb no faster than 100 feet per minute. A Messerschmitt Bf-19E, with its Daimler-Benz engine and variable pitch VDM propeller, was hitting nearly 3,500. British pilots, exhausted and desperate, had begun to improvise. They would take off in fine pitch for maximum thrust, then manually flip a switch to coarse pitch at altitude. But one mistake, one wrong setting in a dogfight, and the Merlin engine would overspeed, tearing itself apart. Air Chief Marshal Dowding summoned the Ministry of Aircraft Production. His order was blunt: find me a propeller that can think for itself. The British engineers stared at one another. There was only one design that could. Within days, a message reached Hartford, Connecticut. Request immediate production license. Constant speed propeller, Caldwell type. It was the beginning of one of the most frantic industrial efforts in modern history. July 1940. Hamilton Standard, East Hartford. The telegram arrived at dawn. BRGMRPOR, Bereitschaftsjahr Manestarishtawar Requests 4008 DRO Mati Units VRs VVADN Hariko Varsio Dilivaro Iron 90 device. Caldwell read it twice. 4,000 propellers, each composed of 250 separate machined parts. Within 3 months, every subassembly, pistons, gears, blades, governors, had to pass endurance testing. And shipping them across the Atlantic during wartime meant losses to submarines were guaranteed. 4,000 in 90 days. His foreman muttered, "That's not manufacturing. That's a miracle." Caldwell didn't argue. He simply said, "Then we'll perform one." The plant shifted overnight to a war footing. Engineers slept on benches. Families brought food to the loading bays. Local machine shops across Connecticut were conscripted into the supply chain. Blueprints were shared with de Havilland Aircraft in Britain, allowing the hydromatic system to be built under license in English factories. Each completed propeller was boxed in pine crates marked Defense Pioa 1, Bereitisagawa MMNT. The first shipment left New York Harbor under convoy on July 22. 10 days later, the Battle of Britain began, August 8, 1940. Biggin Hill, England. Flight Lieutenant John Ellison wiped oil from his goggles as ground crews swarmed his Spitfire. New prop. One shouted over the roar of a fuel truck. American constant, speed job. The Yanks say it'll climb like a rocket. He laughed. I'll believe it when I see it. Minutes later, Ellison pushed the throttle forward. The Merlin engine screamed, but the propeller's blades adjusted automatically, holding steady RPM. The plane leapt from the grass strip in half the usual distance. He banked upward, 3,000 feet, 6,000, 10,000, without touching a control. The climb rate had doubled. When German bombers crossed the channel that afternoon, the RAF met them at altitude for the first time. By late August, nearly every frontline Spitfire and Hurricane had been converted with constant speed propellers. The effect on combat was immediate. British pilots could now climb out, dive, and stay in the fight longer than their opponents. Fuel use dropped. Engines lived longer. A dogfight no longer required delicate throttle, prop coordination. It was instinctive. Air Chief Marshal Dowding's report to Churchill read, "Performance improvement beyond expectation. The constant speed airscrew has given us tactical parity, and in some cases superiority." Churchill's reply was brief. "Send my gratitude to the men in America who made this possible." But for Frank Caldwell, the telegram that mattered most arrived not from London, but from an RAF squadron leader who had survived against impossible odds. It read, "Before the new propeller, we fought to reach the enemy. Now we fight them on our own terms. You have given us our sky back." Across the Atlantic, Hamilton Standard's factory became a city of light and motion that never slept. Railroad cars delivered aluminum ingots by the ton. Women assembled pitch, change governors with surgical precision. Teenagers operated lathes that cut blade roots to tolerances finer than a human hair. By 1941, production reached 10,000 propellers a month. Hamilton Standard supplied not just Britain, but America's expanding air fleet. The P-40 Warhawk, B-17 Flying Fortress, B-24 Liberator, and the soon-to-be legendary P-51 Mustang. Each bore the signature hydromatic hub at its heart, a hydraulic brain that translated horsepower into victory. When America entered the war in December 1941, the demand became incomprehensible. General Motors, Chrysler, and Ford converted entire factories to build engines that would spin Caldwell's propellers. The United States Army Air Forces would need more than 350,000 of them before the war ended. The logistics bordered on the absurd. Propellers for the B-29 Superfortress, each weighing half a ton, were shipped by train from Connecticut to Seattle under armed guard. Each hub was sealed in wax and immersed in nitrogen gas to prevent corrosion during Pacific transport. Hamilton Standard grew from 800 employees in 1939 to over 22,000 by 1943. April 1943. Newthampstead Airfield, England. Lieutenant Charles Chuck Yeager ran his hand along the polished spinner of his P-51B Mustang. The propeller gleamed under the pale English dawn. "You know what the boys in the shop call this thing?" his crew chief said. "Caldwell's clockwork." Yeager grinned. "Well, it keeps pretty good time." That morning, he escorted bombers deep into Germany. The P-51's combination of a Rolls-Royce Merlin engine and Caldwell's hydromatic propeller allowed it to cruise faster, climb higher, and fly farther than any fighter in the world. By 1944, it could reach Berlin and back, a feat once deemed impossible. The Luftwaffe, drained of fuel and pilots, never recovered. Meanwhile, back in East Hartford, Caldwell rarely left the plant. The war consumed every hour. He refused a promotion, insisting he could do more in the test lab than in a boardroom. His colleagues joked that he only recognized the seasons by the thickness of the factory air. He was there the day a new statistic came in from England: average climb time to 20,000 feet for a Spitfire with the hydromatic, 7 minutes 42 seconds. Without it, 11 minutes 8 seconds. The difference was the difference between intercepting a bomber formation and watching it destroy a city. Caldwell quietly folded the telegram and placed it in his pocket. By late 1944, the Allied air forces had achieved absolute air superiority. From the beaches of Normandy to the skies above Berlin, bombers filled the air in endless formation. Every engine turning in perfect, synchronized rhythm. Every propeller blade adjusting its pitch automatically hundreds of times per minute. The roar of that collective power was the sound of a weapon no enemy could match. Not just the muscle of industry, but the precision of mathematics and the patience of an engineer who refused to stop improving his design. May 8, 1945, Victory in Europe Day. Bells rang across London. Flags unfurled from rooftops in New York, Paris, and Moscow. At the Hamilton Standard factory, workers poured into the parking lot, still in their overalls, as the announcement came over the loudspeakers. The war was over. In the test hangar, Frank Caldwell stood beside a final production propeller, hands resting on the cool metal of a blade tip. Around him, the noise of celebration echoed faintly. He thought of the pilots who had trusted his design at 30,000 feet. The crews who had flown through flak over Hamburg and Tokyo. The letters from airmen who had written to thank him for the seconds his invention had given them. The seconds that meant survival. For the first time in years, he allowed himself to rest. Post-war, Hamilton Standard converted to peacetime production. Airliners like the Lockheed Constellation and Douglas DC-6 carried passengers across oceans, their engines still turning Caldwell's propellers. He never sought fame. When asked what invention he was proudest of, he said quietly, "The one that worked." In 1946, the National Aeronautic Association honored him with the Wright Brothers Memorial Trophy for notable contribution to the progress of aviation. That same year, engineers at Rolls-Royce calculated that Caldwell's constant speed propeller had saved Allied aircraft over 1 billion gallons of fuel and increased operational range by more than 10 million miles during the war. A single design, conceived in a small Connecticut workshop, had helped change the course of human history. 30 years later, when historians asked RAF veterans what had made the difference during the Battle of Britain, many spoke of courage, radar, and leadership, but one pilot, squadron leader Eric Locke, put it best. "We got better machines, yes, but it was the propellers that gave them life. Without them, we might have lost the war before it began." Today, in the Smithsonian Air and Space Museum, a polished Hamilton Standard hydromatic propeller stands beside a Rolls-Royce Merlin engine. The placard beneath it reads simply, "Constant Speed Propeller." Designed by Frank W. Caldwell, gave Allied aircraft the power to climb higher, fly faster, and endure longer. Visitors walk past without knowing that within those metal blades lies the quiet brilliance of a man who turned mathematics into motion, and motion into victory. For every turn of every propeller that carried freedom across the skies, there is a trace of Caldwell's relentless pursuit of perfection. His invention did not roar or flash like the engines it served. It simply turned, steady, invisible, unstoppable, and because it turned, the world kept turning too.